So my name is Louis. So I'm a professor of pediatrics at University of Illinois, Chicago. I take care of kids with sickle cell disease and also do research and education. And this is my 30th year in practice. Um, and so during my career, I've had chances to do math models, mouse models, clinical trials, and then now most of my career is devoted toward education and trying to help people to understand the kind of treatments, options, and issues there are in sickle cell disease, including to middle schoolers, to people in west side of Chicago, people in Western Africa, people in Eastern Africa, people in Southern Chicago, and now in Texas. So trying to pull up my slides now and launch into this. Where Teams has got me kind of confused with. Okay, so I'm going to try to share my screen. Can you see my screen? Can people see my screen?
Yes, we can.
Okay. And can you still see my screen? It says overview of sickle cell disease treatments.
You need to make it bigger.
Can you see this?
Yeah, I can see.
Okay, great. All right. And all right. Something's funny with my presentation. So here's my disclosures. I do some consulting, I do some research. I'm really going to try to talk about FDA approved treatments. And the kind of presentations you guys are going to get today is about the same as I gave for a Department of Health and Human Services advisory committee a week ago. So you guys are now at the level of advisory committees, okay, whether you want to or not. The hallmark of sickle cell disease is this severe acute pain. And this pain is depicted here where the artist who has sickle cell disease said, this is the meaning when you ask me how bad is my pain, and they say, tell me on a scale of 0 to 10, with 0 being no pain and 10 being the worst pain imaginable. And I say 10. Well, so this painting is called 10 Redefined. And so as an artist, he's depicting what the severity of sickle cell pain looks like. Tears, screaming, not able to think about anything except the pain. And so all around him are red blood cells that are kind of round and filled with hemoglobin, the molecule that carries oxygen. And then some you can kind of see are purple, blue, they're deoxygenated, and they're kind of elongated shape, and that's the sickle red blood cells. So severe pain is one of the things in sickle cell disease. This pain is said to be more severe than a broken leg, more severe than childbirth pain, similar in pain to kidney stones, the worst pain you can imagine. Now, why is there pain in sickle cell disease? Well, the classical understanding is this kind of thing here, that under the microscope, the red blood cells normally are shaped round, kind of like a jelly donut. You can see those guys there. But some of them have this elongated shape, kind of like a banana or like a chili pepper. And those are the sickle red blood cells. They're also shown on my tie. I don't know if you guys can see myself on the screen anymore, just the screen itself. But the severe pain is felt to be related to these guys here. And so I'm going to try to jump from that to back to my self here. Okay, can you see my camera again?
No, let's see if
Waving.
black screen.
Oh, it's still showing the screen. Okay. All right, one more time here. So now this is me again?
No,
No?
I just came to screen. Nothing on the screen.
This is going to be difficult. Okay, well, we will skip that part. We'll continue with share screen then. Okay, now we're back to the PowerPoint, I hope. Okay, so I will send to you at the end a small video which talks about the different aspects of looking at red blood cells, looking at how they get stuck in the circulation. But what the things have basically done is showed that in sickle cell disease, you have problems with both how smooth or sticky the red blood cells are, how much the blood vessels get tight, and how much hemolysis is going on. The red blood cells break, kind of like a dried chili pepper breaks and releases its seeds. The sickle red blood cell can also break and release its hemoglobin, and that is inflammatory, oxidant stress, and bad for your circulation, bad for your whole body. And so all these different things have now been developed into answers, into solutions where there's different medicines available for treatment of sickle cell disease, shown here, hydroxyurea, glutamine, voxelotor, and crizanlizumab. These are different medicines. The crizanlizumab attacks the stickiness of the red blood cells. The voxelotor and related compounds relate to how much the red cells break down. The glutamine helps with the oxidant stress. Hydroxyurea helps with how much the cells sickle, how much they stay better hydrated. And so all these treatments are now available, which is really, really good news. And it's the result of a lot of research. These treatments also help with different organ damage and different issues where solutions are now being found for the infection susceptibility of sickle cell disease. Shown here is the fever part. Lung disease of sickle cell has some solutions too. Spleen problems, we're still getting there. Stroke, there's ways to try to prevent stroke in sickle cell disease. And kidney disease, there's ways to now slow it down. So it takes special health care, but having solutions for all these different parts of the body is part of the progress and the advances in sickle cell. It does take a lot of specialty care. Some of my patients have 4 appointments with doctors in a month, also expensive. But the outcomes have been people been able to grow up and have families and go to school and work and stuff like that, become grandparents even. And so there are people with sickle cell disease who are doctors, who are musicians, who are actors, presidents of universities. It's been really, really remarkable how much advances there are in sickle cell disease, but it does take a lot of care. And so here's, again, multiple different parts of the body can be affected. And if you don't get sickle cell care, then unfortunately, early death is a strong possibility. So in places where sickle cell disease care is not so available, such as parts of sub-Saharan Africa, including Uganda, where Dr. Mbiru is from, the lifespan of babies born with sickle cell disease is pretty bleak, can be like less than 5 years old, as opposed to the people who are growing up in the United States, like I said, to be 40s, 50s, 60s. The big advance first in sickle cell has been with newborn screening and diagnosis. And so newborns, all newborns in the United States are screened for various newborn types of conditions, thyroid conditions, fetal chenonuria, but also sickle cell. And so whether your name is Gabrielle or Justin or Cesar or Lee, you will get screened for sickle cell disease. And this baby will then have a diagnosis if they have sickle cell disease from very early on, so you don't have to be guessing. This has led to some of the biggest advances in survival for sickle cell in places where the screening is done. In places where the screening is not yet there, such as in Uganda and other parts of sub-Saharan Africa, again, the first way that family might find out that their child has sickle cell disease is that they have severe, severe pain, or they have actually a severe infection, which could be life-threatening. So it's much better to do early detection and prevention. Now, here's a quiz. Does sickle cell disease only occur in people of African origin? Is that true or false? You guys are very quiet.
Almost.
All right, you all got it correct. The answer is that it is not only in people of African origin. It's disproportionately so in the United States, but there are people who have sickle cell in Syria and Lebanon, people in Saudi Arabia, people in Spain, people in Pakistan and India. And so there's lots of people with different places. It is a genetic condition, and it turns out that there's a health benefit to sickle cell trait. So if you have one gene for sickle cell, that actually helps you to survive where there is a lot of malaria. Malaria is a big, big problem in large parts of the world. 3,000 children per day getting killed by malaria. So if you have anything that can help you survive malaria, it's good. Before there were medicines, there's genetic conditions that have helped people to survive malaria. One of them is sickle trait. Another is G6PD deficiency. Another is thalassemia trait. So the trait, having one gene for sickle, helps you to survive and then grow up and pass along your gene to your children so that they too can survive. But it is a myth that it's only African Americans who get sickle cell disease. It just happens that in most of the world, the people who have sickle trait have been from the parts of Africa where there's a lot of malaria. But you can see on this world map that there's other places where there's sickle gene too, shown here with the more intense colors is more where there's more gene for sickle cell. And it does include Nigeria, Democratic Republic of Congo, but also India, also Brazil, also large parts of Central America and the Caribbean, and parts of other continents now, as people have migrated either due to economic reasons or due to slavery or due to war. And so the genes for sickle cell have been spread all over in different places. There has been reports of a child with sickle cell disease in Hong Kong. There's children with sickle cell in Sweden, which hasn't even showed up on these maps here. You know, those are still showing no intensity. Sickle cell disease was first described in the Western medical literature about 100 years ago, 114 years ago in Chicago, in a dental student from the Caribbean who came to dental school in Chicago, and somebody did the new test of looking at his blood under the microscope and found that there were these unusual shapes. But was it actually just discovered in Chicago? Not really. So in different parts of Africa, there's different descriptions in these different tribal languages about how there's a condition that causes severe pain, that causes people to scream and to cry, with names of this disease kind of sounding like the crying of a child. Can't really pronounce it, but tree, 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 or doi, doi, doi would be like a pain cry. There's other descriptions where there's families where a child is born and at a very early age dies, and then their next child is also born and an early child dies. And this is felt to be either some sort of a spiritual, ghostly type of thing, or some child who's sacrificing themselves for the family. There's all kinds of different stories and legends about this. And this is felt to be probably a description of sickle cell disease that runs in families, early childhood death. Some of this early progress in sickle cell, like I said, was related to the newborn screening, that if you did have a baby who got diagnosed with sickle cell disease, then you could also do an intervention starting with that early age, put the child on penicillin daily to slow down the risk of, slow down bacterial infection so that the risk of dying of infection would not be so big. This has been in place since the 1980s. So 1986, this was published, and then it was instituted across the US about a couple years later. So pretty much before most of you were born. And with this, the survival, the lifespan for people with sickle cell has risen markedly over the decades. So back in the 1910s, 1940s, survival you can see in the United States is less than 10 years of age. But after this penicillin prophylaxis was introduced in the 70s, 80s, then survival is now well into adulthood. And this graph ends at 2000. The life expectancy now is probably 45, 50 still. It hasn't risen all the way up to the level of all Americans. So it's still a couple decades shorter than the general population, but it is much, much better than it was before. We talked about the hallmark is severe pain, and there's all kinds of different problems with the pain of sickle cell disease, where the person is expressing their pain, but you can't see anything on the outside. You're not seeing a broken bone sticking out. You can't see anything on x-ray. There's no lab test that shows you how bad this pain is. You just have somebody who says, I'm in a lot of pain. And if it's a child, people kind of believe them. But if it's an adult and they're Black and they're in the urban US emergency department, they get met with skepticism, unfortunately, and get met with stigma like, yeah, right, you're having pain and you want narcotics. I think you're just trying to get high at my expense. I'm not really sure that's what you've got. I'm going to treat you with suspicion rather than with compassion. Very, very, very unfortunate. And so this is one of the things that's led to health disparities. And then the other part is, if you're Black or brown in the United States, there's lots of health disparities, social determinants of health, poverty, transportation, hospitals that are crowded, ERs that are crowded. My hospital emergency department is sending out almost daily warnings and notices about how overcrowded they are and how people have to wait in the hallway or overnight waiting for a bed in the hospital because there's too much crowding. So all these disparities were described in sickle cell disease as manifestations of urban problems, of racial problems, as well as genetic issues. And all the news in sickle cell disease was bad news. It was bad news, bad news, bad news, bad news. And burdens is what people talked about, shown by this child carrying this gigantic sickle cell on their back, how much the sickle cell disease was really weighing upon them, causing them problems. But now there is good news. And I'm really pleased to say that there are now progress in addressing the health disparities, the inequities. Some of the things are having dedicated sickle cell centers. This is a picture of the sickle cell center at my place. There's also progress with more research and treatments. I mentioned that early in my career, I worked with sickle cell mice. So once you have a laboratory mouse that gives you a model of sickle cell disease, you can do research to test things with mice who do volunteer. So you can go from test tubes to mice before you actually get to people and see whether things work before you put people at risk. And so many, many treatments have gone through this, and it's still more is still coming, looking at these different ways to help sickle cell disease. And now this is the part where it gets even more exciting. This is a genetic condition, but there are possible cures. Here's a picture of the skyline of Chicago a year ago with a big bold sign that says cure sickle cell. So here's the conceptual picture of what treatments for sickle cell disease kind of look like. On the left-hand panel is somebody with sickle cell and what their blood picture kind of looks like, that they're untreated, their red blood cells are kind of sparse, so they're anemic, and it's untreated sickle cell disease. They're just fending for themselves with trying to take care with lifestyle choices, no medicines at all. The middle panel would be if you have somebody with sickle cell disease who is taking a medicine, one of those 4 medicines that I talked to you about, that changes the sickle red cells a little bit so they're not so damaged, not so sickling, not so dry, not so much oxidant stress. It improves things, but there's still sickle red blood cells. And so you have a sort of a change shown by this, overall change in the color, but the red cells are still there. And then the right-hand side would be if you take somebody with sickle cell and you give them blood transfusions. If you put normal donor blood into a person with sickle cell, then there's this little patch in their whole blood system of normal red blood cells, shown by the more intense red. And if you transfuse more, you could have more blood there, but you still have this background of sickle red blood cells present. But what could cure sickle cell disease? What would it take? Well, because the blood cells are made in the bone marrow, that spongy, orangey, brownish type of stuff in the middle of your bones, that's where the genetic message for sickle cell gene is, and that's where the blood cells are made. So as long as you have your own bone marrow, you continue to make sickle red blood cells. But if you find a donor with a different genes in their bone marrow and you have their bone marrow transplanted into you, there's stem cells that make more blood cells, could basically make their genetic message of blood cells instead of the sickle blood cells. The ultimate other way to cure this genetic disease would be to have the genes in your bone marrow no longer give the message to make sickle red blood cells. And so gene therapy is the other way to cure. And so the conceptual thing here would be on the far right that you have either complete replacement of your whole bone marrow with the kind that doesn't make sickle red blood cells, shown by the complete replacement of all the blood picture with the more intense red, or you have a partial. The majority of your blood is now made by this new bone marrow or the genetically modified bone marrow. You still have a little tiny bit of sickle red blood cells being made, but it's such a small proportion that that's okay. It doesn't matter very much. It's not causing you problems. That would be called the difference between myeloablative, myelo meaning bone marrow, ablative meaning wipeout. So the far right would be wiping out all your marrow and replacing it 100% with the new cells, new stem cells that don't have the sickle message. Not myeloablative, the second to far right, would be not completely 100% replacement, but like 70, 80, 90, 95% replacement. You didn't wipe out everything, but you did get most of it. The difference between these two, by the way, is kind of the difference between what is necessary for cancer treatment, bone marrow transplant, versus for sickle cell bone marrow transplant. So for cancer, you do want to wipe out 100% of the bone marrow where there might be 1 or 2 cancer cells. You want to get rid of them. You want to have no cancer cells left. Whereas for sickle cell disease, if you still have some sickle blood, but the vast majority is not sickle blood, that's okay. They can still be there. It's not like a cancer that's going to overtake you. As long as they maintain this same balance, that's all right. What does bone marrow transplant look like? It's not a surgery. It's not like you can schedule it for 3:30 on Tuesday afternoon and be done by 7. This is a long process that usually takes months and about a year out of your life. There's a preparative plan where you get chemotherapy, sometimes radiation, sometimes immunosuppression. There's blood transfusions involved. The stem cells are injected where that spike is, and into you when you have a basically empty bone marrow or largely empty bone marrow. And then these new cells have to take up kind of like seeds in a newly plowed field. They have to grow. And while you're waiting for them to grow, you're open to infections. You don't have any blood cells to fight off infections. You're open to bleeding because you don't have the blood cells to stop bleeding. You don't have enough red blood cells to carry oxygen, so you need blood transfusions. And so all these things are while you're waiting for these stem cells to come up, which is about a month in the hospital. There can be some pain, there can be some organ damage during this time also. And then gradually you recover, but it's an uphill period where you need a lot of care. And you might be coming to the clinic once, twice, 3 times a week, like Monday, Wednesday, Friday, coming back to clinic. Not like it's really conducive to going to school or raising kids or going to work. During this period, still watching for rejection of the new cells, but gradually expecting that they're going to be growing up and starting to do their job, and making the new blood cells means you can peel off some of the transfusions or the infection treatments or the rejection treatments. And then finally, you get the long term where things are working, but you need to watch for rejection. You need to get your immunity restored. And so people basically start their childhood vaccines all over again, watching for organ damage, watching for the secondary effects of chemotherapy or radiation on cancer risk, on fertility risk, but people have much, much better quality of life. Here's an example of what the scenario could look like. So here is on the left-hand side, a guy who was at this time about age 16 with sickle cell disease. And on the right-hand side, his sister, who was his donor. And she has sickle trait and he has sickle cell disease, and she's donating her cells. You can kind of see that she has 2 arms busy. Each one has a line in it. The one with the heat pack has blood coming out, and the other arm without the heat pack has blood going back into her. And then in between, it's going through this machine that's in that corner of the room. And you can sort of see this little bag in the upper right-hand corner. I don't have a pointer right now, that is collecting her cells up there in that bag. Those cells will then be harvested for a couple hours, and then all the blood goes back into her still, and then comes out, and more goes through the machine. A little bit goes up into the bag, goes back into her. She's just making a goofy face like any 8 or 10-year-old would do when they're looking at a camera. And then her bag of cells gets moved over to his room, and then infused into that line that's sticking out of his shirt. You see that line on his chest? Special line where it'll go in to find their way to his bone marrow and then grow up and make her type of blood cells, which is sickle trait red blood cells. This was successful for him. He went on to be quite healthy and joined the military. That was his dream. She grew back her cells, and she felt really good for having helped her brother be cured of sickle cell disease. And so that's what happens if you have a donor. But what if you don't have a right donor who's a full match, immunologic match? Well, sometimes there can be a half match, or in your family, or somebody there's an unrelated person is a match for you. And those are possible ways that are getting a lot of research and progress too. And overall, the stem cell transplants from a donor are having quite good success, with overall survival 96%, survival without sickle cell disease 90%. But there are problems with graft versus host disease where the new cells start to attack the rest of your body, or there could be failure of the graft, that the new cells don't grow, like you planted the seeds in the earth and nothing grew. And that can happen about 5% of the time. The chances of that happening is much less if you're a younger person, less than 13, and then having a matched sibling donor is better than other kinds. So this has been worked out quite a bit. Close to 3,000 people have had these transplants. 90% is pretty good, but it's not 100%. So this is not a walk in the park. It still has some risk involved. And then what if you don't have a donor at all? So now there's this new set of approaches called autologous, where your own cells are taken and then the genes are edited. Remember, edited or fixed in some kind of way so that they don't make sickle red blood cells. This was predicted way back in the 1950s when sickle cell disease was first described as a DNA type of condition. And this guy won Nobel Prize for this, Dr. Linus Pauling. And my father was a grad student in Chicago in the 1950s He was studying chemical engineering, but he said that everybody who knew anything about science wanted to know about DNA and about proteins because that was the latest, greatest stuff. And he remembers sitting in a seminar in something like 1958, hearing Dr. Linus Pauling describe this condition called sickle cell. You see that on the blackboard there, and how now that we know what the reason for sickle cell disease is in the DNA, it's just going to be a matter of time before there's genetic cures for sickle cell disease, 1958. So my father, who's now in his 90s, is very pleased that his son, who is in his 60s, has been able to participate in this long journey of sickle cell disease to finally get to gene therapy. And here's what it looks like. And this, again, this is some of the stuff I was presenting to Department of HHS Advisory Committee. The ways that cures can be done in sickle cell for gene therapy can be by adding new genes or can be by editing the current genes. How do you add genes or how do you edit genes? There's two main strategies shown in the gray and the green. So with the gray, you take a new genetic message, a short segment of DNA, a new gene, and you put it into a viral vector as an envelope that delivers that message to a specific place in the DNA. Like an envelope does, it sends it to an address. It doesn't send it to a random place. And then opens and inserts that there. And then you have a new gene for a new hemoglobin, such as hemoglobin A T87Q, that blocks the sickling process or does something else to make the cells not sickle. So that would be adding in a new gene with a viral vector. The other approach, shown in the green, is called gene editing. Here, instead of putting in a new message, you're actually either snipping out something or you're doing kind of like a word processor, find, replace, or find, cut. And many of these have been able to change the regulation of your hemoglobin so you don't have as much of the sickle hemoglobin there, or you have more fetal hemoglobin there. These are two really, really high-tech processes, and I don't have time to go into that, but the concept is shown here. The results are amazing. The results have been really, really good. So that you have people who, as shown in this TV segment, this young lady used to be basically in the hospital all the time. All her life was spent in and out of the hospital with pain and seeing doctors and getting pain meds. But after gene therapy, she's doing martial arts. She's looking quite good. Similarly, New York Times had articles about this, how people were really desperate for treatment and they signed up for gene therapy as experimental treatments. What do the experimental data look like? Like this. This kind of graph is called a swimmer plot. And the concept is that each lane, each horizontal, is one individual going through a period of time, shown on the x-axis from minus 24 months to 0 months is when they got their gene therapy, and then following them out 36 months. And so this person in their lane is having different experiences, and you can see what the impact of the gene therapy at time 0 is. Even though they had them at different times of the calendar, you line them up for, they all have pre-gene therapy and post-gene therapy this amount of time. So in the time before gene therapy, minus 24 to 0, you can see that each individual had lots of dots in their lane. And each dot represents some kind of pain event, a hospitalization, an intensive care unit stay, an emergency department visit. And the number of dots would represent when and how many times they had to get that kind of pain treatment. And so you can see some people have like 7 dots, some people have 20, some have a cluster of them and then a gap and then a couple more. But then after time 0, when they had their gene therapy, look what happens to the dots. Most of the people really have no more. And the ones who did, there's like a handful. So out of all the people on this graph, if you look at the median number of pain episodes shown in the very bottom, 4.0 pre-gene therapy, post-gene therapy, the median is 0.0. Makes their pain basically go away. You remember that pain that I was telling you, 10 out of 10 pain? Can you imagine be freed of that pain? That's what it's meant for these folks. So this has been really, really helpful. There's all kinds of different strategies to do it. Shown here is that 2 of them were very successful in their clinical trials, the 2 in green. The next 3 rows still in clinical trials. The bottom 3, 4 rows withdrew from the clinical trials because they weren't getting such good results. But the 2 gene therapies that were in green did get approved by the Food and Drug Administration as actual treatment in December of 2023. So almost exactly 11 months ago. Hasn't been a whole year. And so one is a gene editing version, one is a gene addition version. Are these cures? Right now, we say they are potential cures because there's been data you saw in this swimmer plot. Some people reach 3 years at the time of this slide. Since this slide was made, time has elapsed, and there are some people who made it to 5 years, but still the amount of time is limited. And so we're really waiting for a longer period of follow-up before we completely say that this is a cure. So the terminology right now is potential cure, while waiting for years and years of follow-up. How much does it cost? A lot. One version is 3.1 million, another is 2.2 million, and that's not even counting the hospitalizations. But there's been analyses that show that this actually can be a savings to society, that there's less medical costs for the entire person's lifetime because you're not getting hospitalized for pain, not having to get treated for all these different kinds of things. And there's indirect benefit to society with fewer absences from work for both the individual with sickle cell and their family. You may have seen ads on TV for other kind of conditions where, like, oh, where's Phil? He can't be at the birthday party today. How come he can't be at the graduation? How come he can't be at sister's wedding? Well, it's because he's sick with this, that, and the other thing. And then they get this new miracle treatment, and now they're smiling and they're part of the group picture. Similarly, showing up for work can be much, much better after you've had these kinds of treatments. And then there's questions of, does everybody want to go to gene therapy? And the answer right now is not everybody, not yet. Part of it is that we're not sure who really should get referred. There's treatments, the eligibility criteria that were set in the clinical research studies were for age 12 and up. So if you're too young, you might not be eligible. In the clinical research studies, there was upper age limits of like 35. And there's some people who might be interested in gene therapy and they're 36 or 40. Right now, they probably would not go. Some people have kidney problems and they may not be eligible because the medicines to prepare your body or the medicines to fight rejection depend on really good kidney function. There's side effects that people worry about. And so some people worry that, well, if I have a risk of cancer in my family anyway, and I get this treatment that does raise your risk of cancer, will I be pretty much trading off my sickle cell disease for future cancer? There's some people who have chronic infections, such as hepatitis C, that may not be able to tolerate having a weakened immune system during that time where you're waiting for your new cells to grow up. Some people don't want transfusions, like Jehovah's Witnesses, for religious reasons, object to blood transfusion. So for them, having any kind of treatment plan that involves blood transfusions is a no-go. And then I've had 1 or 2 patients who said, my hair means a lot to me, and any kind of treatment that involves hair loss is just out of the question. That's not something that I can do because my hair is part of what I am. Infertility up in the upper first line can be dealt with. You can have freezing of eggs or sperm and storage of them. There's technology to do that. It does cost money, it does take time, but it can be done. So infertility is not exactly a no-go, a risk of infertility. But costs and insurance can be a big thing. Nobody really has, or very, very few people have $3 million in their pocket ready to spend, even for something that's life-changing. But the good news is that insurance companies like Blue Cross Blue Shield and federal insurance organizations like Medicaid, Medicare are preparing to pay for this. They haven't quite worked out exactly how they're going to pay. And so right now it's case by case, and there's a whole lot of lawyers involved about, well, if there's going to be a $3 million cost, at what point do I pay that $3 million to the company? And what point do I pay it to the hospital? Do I pay when everything is successful and done? You might do that for a contractor who's doing construction on your house. Do you pay up front? Or do you pay in installments, like you might pay for a car or pay for a house? Those kinds of things are still getting worked out. Should government support sickle cell disease completely, as we're going to put all our money into gene therapy as opposed to emergency department care or medication treatment or newborn screening? Well, no. People should not continue to have organ damage and problems while they're waiting for the gene therapy, because you can't all go to gene therapy at once. And then there are some people who might not be able to go. Does it work for all types of sickle cell disease? That's still being resolved. Is it safe? That's still being resolved. What questions should I ask my doctor? We're trying to educate the individuals with sickle cell as much as we can. But in some cases, people have come back to the Sickle Cell Disease Association of America as an educating group and said, you know, I had more information than my doctor did. When I started asking my doctor, my primary care doctor had no idea about sickle cell gene therapy. I have to only go to the gene therapy center to get my questions answered. And then finally, is this the first community to get gene therapy? Yes and no. So gene editing, yes, this is the first disease ever to get gene editing therapy. But gene addition has been already used for all these different lists of conditions, some of them quite rare, successfully, and have been done for other kind of people, other kind of conditions. You can learn more at these kind of websites. I'm going to send this presentation to Dr. Biro, so you can go click on them and look them up. You can also look at the SCDA website, Sickle Cell Disease Association of America. I was chief medical officer until 2 weeks ago. For 4 years, I spent doing education and trying to prepare different ways of informing patients about this. But overall, the optimism is just enormous for sickle cell disease, and much of what needs to be done is education to let people know about all the progress that's being done. And I will stop there and see if I can go back to screen. Stop sharing. Oh, this is doing my camera on the other side. Okay. Well, anybody have questions?
Thank you very much, Mr. Professor. Thank you very much for the talk. Let me see that. If we have any questions, okay. I have a question. How many patients have been treated with the new treatment that you know? Not for experimental, just after it was approved.
One has completed it in Washington, D.C. There's another 3 or 4 in the works. The barriers have been getting lawyers and insurance coverage to all agree. So if you look in the news, look for a 12-year-old in Washington, D.C., Children's National Medical Center was patient number 1.
So not so many have taken over, have taken.
Exactly. It takes brave pioneers still, even though it's not experimental clinical trial anymore. This is still relatively new. So the first kid was, I think I mentioned 12 years old was the lower age range for this. And in bone marrow transplant, the decision or the data shows that under age 13 has the best results. So at Children's National in DC, they chose to go with the youngest possible that they could find. And so they picked a 12-year-old. Other places have 20-year-olds, teenagers, and then a few have other, most of these gene therapy centers have a waiting list of people who are lined up waiting for their insurance approval for other kinds of things to get set up.
Now, where are the treatment centers available? Do we have one in Houston?
Do you have one in Houston? I'm pretty sure you have at least one. I'll need to send you the map for that.
Any more questions before we go into the other part?
Yes, I have a question.
Yes.
One is very basic. The other is very, very foundational. And the other one has to do with clinical trials. But the first one is one of my students, she was a Hispanic gal. She had the trait for sickle cell. We took her, we pinpricked her and she wanted to see if she could see any sickle cell red blood cells, but we could not see any.
Oh, okay.
So can you explain why we couldn't see them?
Yes. So two reasons. One is that sickle trait usually should not be sickling because inside each red blood cell is a mixture of normal hemoglobin and sickle hemoglobin. And the normal hemoglobin inhibits the polymerization of the sickle so that under most conditions you don't get sickling. And that's a favorable thing. That's why people with sickle trait are not usually sick. The other is that you could subject it to conditions in your lab or in your whatever place you are to make them sickle, but it takes fairly extreme conditions. And so the conditions would be to put it under both hypoxic and oxidant stress and a little bit of acid at the same time. So people will use exposure to sodium metabisulfite and then fix the red blood cells before they have a chance to revert from their sickled shape to not sickled. And so what would happen is that in a red blood cell, if they're subjected to a severe enough condition and you have a mixture of hemoglobin S and hemoglobin A, if you put them under really severe conditions, the S would polymerize and leave the A out. So the A is still floating around, but the S is stacked up into a polymer, and that could make the cell sickle. So there is some tests and situations you could do that.
Okay.
Kind of a long answer, sorry.
No, it was perfect. Thank you. I'll be able to, because I couldn't give her an answer of why we couldn't see them. So that's perfect. My other question was, are there clinical trials for these new procedures that would not really cost the patient?
Yes, very much so. So when there are clinical research studies, they're basically done at no cost to the patient. I had showed, maybe I can find it again, that there are still companies that are investigating. Can you see my screen?
No.
No, not anymore. Oh, well. So there's at least 3 companies that are still doing clinical research in gene therapy. One of my patients is undergoing one of that now. Another is going through another one. And because there's still clinical research, there's no cost involved and it is potential to do. These tend to be at large academic medical centers. You might have to travel to get to that. If you go to either clinicaltrials.gov or the Sickle Cell Disease Association of America has a clinical trials finder. It talks about different research studies that you can participate in and what cities they're offered at. Now, a clinical research study does not guarantee you results, and it is a research study. And so you do have some risk that you're taking on. It's not like you're just going and getting something for free. There's costs and risk involved. And there'll be a long consent process that tells you what risks you're taking. And people need to be thoughtful about that and read a 35-page consent and think about it, talk about it with their family.
Okay, thank you.
Yeah.
Thank you very much.
Because other people have signed up for clinical research, that's how advances have been made. And more, the informed patients, the well-educated and well-informed patients have understood that sometimes it's doing a survey when it's not convenient for you, you still do the survey. Sometimes it's signing up to be testing a new medicine to see if that'll work. So some of my patients have signed up for 3, 4 clinical trials, one after another. Others have done every survey that comes to them, things like that, to help advance the knowledge.
Yeah, then we have a question here.
Yes.
Hi, Dr. So my name is. I'm currently working at a lab. Why is it so important? I'm working like football.
Oh, your voice is breaking up. I'm sorry. Can you get closer or something?
Hi, can you hear me now?
That's better. Yeah.
Okay. Hi, so I work at a lab and sickle cell is a blood test that they do for sports for a lot of students. Why is it so important? Why sickle cell exactly? Like sport, like football.
Oh, wow. Okay. So and this relates to the question that was asked earlier. So in people with sickle trait, under extreme conditions such as dehydration, exhaustion, there can be sickling. There can be also this condition called heat stroke, exertion leading to collapse, basically. So picture like the very first guy who ran a marathon, he died at the end of the marathon. Or picture somebody who's trying to do football practice in August in South Texas in a full football uniform and has not been in shape very much and is being asked to do 2 practices a day. That is exhausting. And if you have an unreasonable coach who doesn't let you drink water, who asks you to push yourself beyond your limits, you could die. And what has been found is that the chances of death is much greater for people with sickle trait than for people without sickle trait under these extreme conditions. And again, it's unreasonable type of extreme conditions, like pushing yourself to finish a marathon when you really can't, or doing football practice when you're not in good shape. So the solutions for this, one is that the military found this happening in basic training camp, and recruits were dying, but they changed their training policy. So instead of having full uniform and do everything all at once, they made sure that people were in shorts at the start of training and that they had to gradually get in shape, and also they had to stay hydrated, and they would limit the afternoon full heat of the sun type of exposures, and they would do training and drills in the cooler parts of the day. The NCAA has not decided to do that, nor have high school football coaches. And they have pushed people to keep on going, and they set up the sickle test to identify who's at greater risk so that they cannot treat them the same way as the rest of the team. You can tell I'm not in favor of the NCAA solution, but that's why there are these tests being done. So people have to do this test in order to tell the NCAA whether I have sickle trait or not. The other thing they can do is sign a waiver saying that I don't want to get tested, I don't want to know, and so forth. But I think that the coaches should instead adopt more reasonable training practice is to gradually do conditioning, stay hydrated, avoid heat exhaustion.
Thank you very much. Any more questions? I think that's what we have, Dr. Sri. Thank you very much again. Let's give us a review. Yeah, thank you. Now, if you can send me the slides, which if
Sure.
you can, at the end of the one, yeah, send them to me so I can pass them to them.
Great. And did anybody from Uganda join?
No, I didn't send a link to them,
Okay,
but I'll send them we recorded it. I'm going to send them the recording.
great. Okay, thank you so much. Thanks for
Thank
having
you.
me.
Yeah, thank you very much. Okay, we'll meet again. Thank you.
All right, bye-bye.
Yes. Bye.